So good morning, guys. Today we're going to continue our discussion on heat transfer via conduction. We're going to spend the majority of our efforts today talking about steady state conduction. I push back the transient discussion to next week just in terms of time and flow. I don't want to start getting so fast and cramming. It's just not going to be helpful for anybody. So from last time we talked about conduction. We had stated, and since I like to have some organization when I take notes, that the heat transfer flux in conduction in a one-dimensional system can be described as the temperature gradient in that direction times the thermal conductivity of the material. When I consider the general form of Fourier's law, I can say heat transfer via conduction is equal to K times the surface area over the temperature gradient divided by the thickness in which heat transfer is occurring. Now, one thing I don't think if I've mentioned yet is signage in terms of heat transfer. Now, the signs in heat transfer and heat are opposite of what you would consider as we've discussed for work, such that if I have, let's say, a system that I've defined as my box when I draw my, my boundary layer around my system, I find that any heat transfer added to my system is positive, and any heat transfer that occurs out from my system to the surroundings is considered negative, such that heat added to my system is positive, and heat removed from system is negative. Ugh, it always likes to jump. And we also discussed last time that I can describe my heat transfer via conduction not only by Fourier's law, but by what's known as a resistance model, where my conductive heat transfer can be essentially the temperature gradient over the total thermal resistance that I have in my system, where conductive thermal resistance is given as delta X over K times surface area, and for problems involving convection, convective thermal resistance can be provided as 1 over H times A sub S. And so this is useful when considering composite systems. So for example, when I had this multi-component wall, I now have different materials of differing thicknesses. And I probably have some form of temperature here and some differing temperature here. Let's say if Ti is greater than To, I know my heat transfer is going to happen in this direction. And I believe I left you last time with a question that asked, will the heat transfer rate in the X direction be the same for each layer?
I said no to that question.
So I got one no.
I would also think no, but also there are other factors such as conductivity of the material that need to be taken into account for a definitive answer.
Okay.
I think it has to be the same, but the temperatures will all be different. Yeah, that's
All
the
right.
answer I'm going to go with too. Different delta T's, but same heat flux through each layer.
All right. We got some yeses, some nos. Well, the correct answer is, if I'm looking at heat transfer that occurs in the x and only the x direction, and I know based on the temperature gradient, it has to go from the high temperature to the low temperature, therefore conduction is going to occur in this direction. And if I do an energy balance over each system, let's say the energy balance over this first system, right? Any heat transfer coming in is also going out, right? As I've drawn it. As the heat's going from high temperature to low temperature, meaning at steady state, there's going to be no accumulation of heat in that first material. And if I draw another system, say this blue, over my second material, all the heat transfer that's leaving my first material is going into my second material. And vice versa, if I do a gray, all the heat transfer leaving, yeah, there it goes. All the heat transfer leaving my second material is going into my third material. And what that means is at steady state, the heat transfer through each layer will be the same. So all the heat going in comes out so that there's no net accumulation. But what we do find, as hinted at earlier, is that, let's see, now I want to clean this up. That's an eraser, not a pen. Thank you, computer, for finding that out. Yeah. I know I made a mess. I'll just redraw it. The beauty of technology. The temperatures that exist will all be different, as you stated, right? So we have a delta T1, a delta T2, and a delta T3, even though the heat transfer rate, Q, will be the same. When that means, when I look at this system, I can say Q is equal to delta T over R total. And what I can also say is in this system, the heat transfer rate is also equal to each individual temperature gradient over the thermal resistance in each layer. And what this allows me to do, to find my R total, that simply becomes the sum of the thermal resistances in each layer, in each layer. And at the same time, my total thermal gradient or temperature gradient is simply just the sum of the gradients in each layer. And this is application of what's known a resistance in series model. We call it that, as you might recall from physics. We can kind of essentially equate this as resistors in a circuit, such that the total resistance is just simply the sum of each individual resistance. Any questions on this discussion? All right, if not.
Are those supposed to be for the Q conductive? Is that supposed to be delta T1 over R1 plus delta T over?
Now they're all equal.
They are all equal? Okay.
Yeah, these are all equal signs. I can make that clear. So let's take a look at an example. So in this example, I have a flat furnace wall constructed of a layer of what's known as silocell brick with a thermal conductivity of 0.089 BTUs per hour per foot per degree Fahrenheit, backed by a 9-inch layer of common brick, which has a thermal conductivity of 0.8 BTUs per foot per hour per degree Fahrenheit. If the temperature of the inner face of the wall is 1400 degrees and that of the outer face is 170 degrees Fahrenheit, what is the heat loss through the wall and the temperature of the interface between the silocell brick and the common brick? So let's take a look at this example together. This is the furnace example. So in this problem, I have, well, it's a composite layer. I have silocell, and then I have common brick. The temperature on the inside surface of the silocell is about 1400 degrees Fahrenheit. The outer surface of the common brick is 170 degrees Fahrenheit. The thermal conductivity of the silocell brick is approximately 0.089 BTUs per hour per foot degree Fahrenheit. That of the common brick is approximately 0.8 BTUs per hour per foot degree Fahrenheit. That means to find the conductive heat transfer rate, I need to identify delta T over R total. And for this problem, delta T is simply 1400 degrees Fahrenheit minus 170 degrees Fahrenheit, which gives us a value of approximately 1230 degrees. R total is simply the sum of the two resistances, R1 and R2, or the resistance in the silocell brick layer and the resistance in the common brick layer. So to solve this problem, I have to identify these two thermal resistances. So the resistance 1 will be a delta X over K times A. The thickness of the silocell layer is approximately 4.5 inches. So I can do 4.5 divided by 12 to give my value in feet. The thermal conductivity we've already identified as 0.089 BTUs per hour foot degree Fahrenheit. Here, my pen's getting a little wobbly. And I need my area. Now I don't have an area, so what I can do is simply just take a basis of 1 feet squared of wall. And to make my calculations simple. So if I do this, I get a value of approximately 4.21 hours degree Fahrenheit per BTU. For my second thermal resistance, I simply have to do the same thing. But for my next material, which has a thickness of 9 inches with a thermal conductivity of about 0.8 BTUs per hour degree foot, foot, degree Fahrenheit, with my basis area of 1 square foot. And this gives me a thermal resistance of approximately 0.93 hours degree Fahrenheit per BTU. Therefore, my total resistance is simply the sum of these two values, which gives me 5.14 hours degree Fahrenheit per BTU, which means with this value in hand, I can then solve for my conductive heat transfer rate, which is simply 1,230 degrees Fahrenheit divided by my total thermal resistance of 5.14 hours degree Fahrenheit per BTU. What I get is approximately 238 BTUs per hour. I'm taking in my basis if I wanted to, per foot squared of wall. So in essence, what we're really solving for is a flux because the A area isn't specified. All right, so the second part of the problem asks, what's the temperature at the interface? Well, to identify that temperature, I know not only does my heat transfer rate equals delta T over R total, it also equals delta T1 over R sub 1, as well as delta T2 times R sub 2. So what I'm really needing to solve for is one of these intermediate temperature gradients. So for example, if I wanted to solve for delta T1, it's simply my conductive heat transfer rate times R sub 1, or 238 BTUs per hour times the thermal resistance in the first layer of 4.21 hours degree Fahrenheit per BTU, which gives me a temperature gradient of approximately 1,006 degrees Fahrenheit. And so the T at the interface is then 1,400 degrees minus 1,006 degrees, or approximately 394 degrees Fahrenheit. Which means what we actually have in this problem is a pretty significant temperature gradient through the silicel, and then a more moderate temperature gradient through the common brick. And so what we find is it's the silicel brick that's actually providing the majority of the thermal resistance, and we see that further evidenced by the values of R through each material. Are there any questions on this problem? If not, we can keep moving and consider how can we describe heat transfer a composite that varies in the y direction. All right, so we're considering heat transfer in the x, but the composite now looks something more like this. What do we expect to occur in this system?
different rates of heat transfer through the different materials, since I'm assuming they'll have different resistances to heat flow.
That's correct. So what we find is that each material will have a different heat transfer rate due to the ability of each materials to conduct heat. And it's really easy to kind of think of if I kind of consider, let's say, the top and the bottom pieces as, insulating materials, and the middle piece exists as like a copper wire, right? In that instance, you would say, well, the majority of the transfer was probably going to go through that middle material because it has a much higher thermal conductivity than what we might expect on material above and below it that would probably have a low thermal conductivity. And so the way that we can describe this, similar to a resistances in series model, is through application of a resistances in parallel model. So what we can find in this system is that Q conductive still equals the temperature gradient over the total resistance. However, the total resistance for systems in parallel now equals the inverse, the sum of the inverse resistances taken to an inverse. And also, Q conduction does not equal what we had identified earlier. If I could spell parallel. And so, for example, if I had a material or a wall that looked like this, why I'm not sure, where there was some initial temperature here, some outlet temperature here, and I didn't know the surface temperatures on the walls, such that I had to consider convective resistance on either side. What I could do is essentially draw an equivalent circuit for this material. And based on the materials, the circuit that I would draw, you can identify how to obtain your total thermal resistance. So if this was R1, R2, R3, R4, R5, R6, R7, R8, R9, you can state that the total thermal resistance is R1 plus R2 plus 1 over R3 plus 1 over R4 to the inverse plus R5 plus 1 over R6 plus 1 over R7 plus 1 over R8 to the inverse plus R9. And so application of this resistance model allows you to kind of break down each material by its thermal resistance and consider how each material's individual thermal resistance contributes to the whole system. Are there any questions on that?
Could you explain why you have like R1 and R9?
Yeah, so these, assuming I don't have the temperatures on the surfaces of the materials, you would have to consider any convection that would occur between the ambient air on the inside and outside as it relates to the surface of the materials. So that would be where we would bring in our convective thermal resistances. Yeah, this is all conduction. And this is convection. That's a good question. Any other question? If not, let's take a look at an example where this kind of system would apply. So in this example, I have a 3 meter by 5 meter wall consisting of 16 by 22 centimeters sectional of horizontal bricks, separated by 3 centimeter layers of plaster, which also contains 2 centimeter plasters on each side of the brick, and a 3 centimeter thick foam on the inner side of the wall. If the indoor and outdoor temperature of the wall are 20 degrees and minus 10 degrees respectively, and assuming that the inside and outside heat transfer coefficients of the wall are 10 watts per meter squared Kelvin and 25 watts per meter squared Kelvin, what is the rate of heat transfer that exists through the wall? So this problem is a little bit more complicated than the first example. So we will go through it together, one step at a time. I'll give you guys a few seconds to kind of jot down some of this information, and then we'll break it down together. Okay, so let's draw this out and take a look. So in this example, we have a brick, and around that brick, we have some plaster. So this is going to be the brick, this is going to be the plaster. And on one side, the inner side of the plaster, we have an extra layer of foam. So we have foam, plaster, and brick. In terms of the dimensions, we can state that the foam layer is approximately what? 3 centimeters. Excuse me. The plaster layers between the foam and the brick are about 2 centimeters. Here, I'll zoom in and make this a little neater. And this brick width is going to be approximately, what do I have in my notes? I think it's 16 centimeters. And the length of the brick, which I will draw here, is about 22 centimeters. And these are 3 centimeters. And then up here is another brick, right? And so the process is kind of like a repeat unit. Which for completeness, I'm kind of just showing you to give you an idea. Right, so it's essentially a brick wall that's put together with plaster that also has foam on the inside of it. The wall is 5 meters by 13 meters, or 15 square meters. And the inside temperature is 20 degrees. The outside temperature is minus 10 degrees, so a little cold. And we have some heat transfer coefficients, 10 watts per meter squared Kelvin, and 25 watts per meter squared Kelvin. So the question is, how do we find the heat transfer rate through this crazy wall? Well, what I would recommend doing is identifying, based off of this wall, what is essentially the repeat unit that exists, such that if I took a slice of this wall, found the heat transfer for that slice, and then scaled it up for the entire wall, I would get the heat transfer rate over the whole wall. And so for this wall, that slice would be essentially here. And so I would draw my boundary for my system kind of like this. And say if I found the heat transfer rate here, I can just scale it up based on that slice over the total area. And so my basis is going to be a 25 centimeter section by a 1 meter section, because I don't know the z, or a basis area of about 0.25 square meters. And so with that, I can say, well, what are the thermal resistances that exists over this whole system? And keeping that in mind and cleaning this up a tiny bit, what I have is resistance on the inside due to convection, another resistance here due to the foam layer, a resistance in this plaster layer, and then since my repeat unit is only 2 materials, it would be these 2 material resistances, another plaster layer, and then the outside heat transfer resistance. And so I'll move this to make it easier to see. So I have convective here, a plaster or a foam layer, a plaster layer, brick layer, another plaster layer, another plaster layer, and then another convection. Does everyone kind of see how I was able to draw that resistance model? and how I was able to define this system. So with that in mind, in order to find the heat transfer through this wall, I simply need to identify each of these resistances to get my total thermal resistance, and then take my temperature gradient over that total resistance. Or once again, Q conduction is simply equal to delta T over R total, where delta T is 20 minus negative 10, or 30 degrees Celsius. Let's go through these one at a time and find each of these thermal resistances. So the thermal resistance in my convection system is simply equal to 1 over HI times A, or 1 divided by 10 watts per meter squared Kelvin, times my area basis of 0.25 square meters, or approximately 0.4 kelvins per watt. Next, I can look at my foam layer and say, well, it's the thickness of my foam divided by the thermal conductivity of the foam times my area, which the thickness of the foam is 3 centimeters, or 0.03 meters, divided by the thermal conductivity of the foam, which given in the problem statement is approximately 0.026 watts per meter Kelvin, times the area of 0.25 square meters. Which, I'm missing that value from my notes. It's approximately 4.62 kelvins per watt. Next, I need the thermal resistance in my plaster layer, this initial plaster layer, 1, and it's also the same, going to be the same resistance in the third, or this one, RP3, because of symmetry. And so I can say each of these layers delta X over K plaster times A, or 3 centimeters. Or is it 3 or 2? It's 2. Excuse me. Divided by the thermal conductivity of the plaster, which is 0.22 watts per meter Kelvin, divided by the area of 0.25. It gives me approximately 0.36 Kelvin per watt. Is everybody following okay, or am I going a little too fast?
You're doing good.
I'm good.
All right, thank you for the feedback. All right, next comes the tricky part, looking at the resistances in the brick and that plaster layer that's in line with the brick. So initially, the brick is going to be the thickness of the brick over the thermal conductivity times the area. The thickness of the brick is approximately 16 centimeters, or 0.16 meters. The thermal conductivity of the brick is 0.72 watts per meter Kelvin. And the area we find is going to be different than our basis because it only covers 22 centimeters of the 25 that we're basing our problem off of. And so the area here is only going to be 0.22 square meters. And this gives us a value of approximately 1.01 kelvins per watt. The second plaster layer therefore, makes up the rest, 0.16 meters, which is 0.22 watts per meter Kelvin, and 0.03 square meters, which gives us a value of, let me double check this, 24.2 kelvins per watt. And then the last thermal resistance we have to find is their final convective resistance, which is 1 over HO times A, or 1 divided by 25 watts per meter squared Kelvin, divided by the area of 0.25 square meters, or 0.16 Kelvin per watt. So now we have all of the thermal resistances in the system, and I'll zoom out so you can kind of see each of them. This one's a little bit of a long problem, but it will be useful for homework as well as looking at how we can apply this resistance and series model. So all we need to do is identify our total resistance expression, which is convection 1 plus convection 2 plus the R of the foam plus 2 times R of the plaster, which is 1 and 3, plus the inverse of the resistance of the brick plus the resistance of the plaster to the inverse. So plugging this in, I get a values of 0.4 plus the 0.16 plus the foam, which is 4.62, plus 2 times 1.01 plus 1 divided by 24.2 plus 1 divided by,
Wait a minute, it shouldn't be 1.01. That
You're
was
right.
for the brick.
yeah, I got those crossed. It should be 0.36. And so this makes our total let's see what that comes out to be. I get about 6.87 kelvins per watt. So a lot of work just to find the total resistance. But now that we have it, we can say therefore our conductive heat transfer rate is simply 30 degrees over 6.87 kelvins per watt.
A different value. I'm not sure if I did it wrong because I got 3.8
Well, let
kelvins
me,
per watt.
I'm more than happy to double check. I got 4.87 twice, or 6.87. So this gives us a value of approximately 4.37 watts. Now this is per that 0.25 square meter wall area. To find the total Q, you just simply got to multiply that area, right, and correct for your basis, right, because it's really 4.37 watts per 0.25 square meters of wall, and the total wall is 15.
Dr. Lopez,
Yes.
isn't the term for the total resistance in kelvins per watt, so we'd have to correct the temperature term for that?
In this
Or would
case,
the
we don't
difference
because
be-
it's a delta degree.
Okay.
And so a delta C and a delta K are the same. Because, you know, I could look at absolute temperatures here, right? Between 20 and negative 10 degrees Celsius, but I'd just be adding 273 on both sides, so they would cancel out. But it's a good question. So if I correct for the area, I get a value of approximately 262 watts. So any questions on that problem?
Where did you get the area for the P2? For the, you got 0.03.
For the plaster, because of the thicknesses here in each of these layers. So if I'm looking at just this 25 centimeter section, I have 22 centimeters of brick and 3 centimeters of plaster. All right, I think that's all we have time for today. We'll wrap up this discussion next Monday and get started on transient heat conduction. So any last minute questions? If not, thank you all for your attention. Have a great day and a great weekend.
Thank you.
Thank you, Dr. Alpitz.
All right, take care.
Thank you.
Thank you.